Hello everyone, it's your favorite chemist, Adrenaline, the Bazooka Prophet. And today I'm going to be teaching you uh, a very interesting aspect under chemical equilibrium, talking about the relationship between the Kp and Kc. Kp, which is the equilibrium constant for pressure, which involve gases, and also the Kc, which is the equilibrium constant for concentration. Now, we should understand that the Kp and Kc of gases, they are usually not the same. And on that very note, there is need for us to understand or to relate the Kp and the Kc. And in this video, I'm going to be teaching you the calculation involved, and I will give you stepwise process in getting your answer with ease. Now, the relationship between Kp and Kc is Kp is equal to Kc. See now, open bracket, the gas constant R multiplied by the temperature in Kelvin, the close of bracket, then change in the number of moles of gases from reactant to what now? To product. Take note that change in mgs, it means change in the number of moles of gases when moving from reactant to product. And if you look at some of the things given to us here, you would relate it with each other. You understand that please arrow varies depend on what you are given to use in the formula or in the question you are going to solve. Why? You can see, as we have rightly said, they will move straightway in solving some important question there. Now the question says, for the reaction given to us here, which is sulfur oxide with oxygen to give me sulfur 6 oxide. Question says, what is the Kc for this equilibrium reaction at 25 degrees Celsius? Given that Kp for the same reaction is 3.4 times 10 raised to 22 kilo per Pascal, and your arrow is 8.314 cubic decimeter kilopascal per mole per Kelvin. It's as easy as that. Now, what do we do first of all? We will recall that a Kp is equal to Kc ROT, change in the number of moles of the gaseous substance, which is the product minus the reactant. Now, we're giving our Kp to be 3.4 times 10 raised to power 22 kilo per Pascal. Then we're giving our RO to be 8.314 cubic decimeter kilopascal per mole per Kelvin. You see, it is not difficult at all. And our change in the number of moles of the gaseous substance is the number of moles of the product minus the number of moles of the reactant. How do we go about it? Now, we have 2 here. 2 minus the number of moles, the summation of the number of moles there is 2 plus 1, which is 3. And it will give me minus what now? 1. You see how it is going? The summation, okay, let me put it here. The summation of the number of moles of the product minus the summation of the number of moles of the reactant. It's as easy as that. Here is 2 and here is what? 3. Okay, minus 1. And we are looking for our K what? Kc. Very, very easy. Now, it means that from this formula, we will make Kc the subject of the formula. I think Kc is equal to Kp over ROT change in the number of moles of the gaseous substance. Please be very, very careful here. I got this Kc, I divide both sides by K, okay? I divide both sides by this one here to give me this. For those persons who might be wondering, I just went in directly. So I come here to now say my Kp here is 3.4 multiplied by 10 raised to the power 22 over 8.314 multiplied by, please take note, your temperature here, let me find the temperature which was 25 degrees Celsius plus 270 will give me 298 Kelvin. So that is 298 Kelvin, and here is minus 1. When you divide, your final answer should give you 8.423. Okay, let's abbreviate 24 times 10 raised to the power what now? 25 what now? That's K then per mole. That is how easy it is. So that gives us our final answer. And on that very note, we come to the end of this aspect. Now, it is very easy. So with this example I just did for you right on the board, you can attempt others very, very easy. Just first of all, bring out what you're giving and look at what you are looking for. Then just go ahead. It is very, very easy. Please, you have not yet subscribed to my YouTube channel. Please do well to get more updates. For now, God bless you.